and then maybe I got the wrong order, but after Heidelberg, you went to CISA?
No, I went to Australia.
Australia first?
To Melbourne.
Melbourne, you worked with Tony Gergeta, part of the physicist, very famous. Actually, Tony Gergeta was almost my classmate in Chicago.
Ah, you study in Chicago?
Yeah. I tell you this later.
Yeah. Almost your class.
So after Melbourne, you went to CISA.
I went to CISA.
Where he worked with Marco Cerone.
Yes.
And after CISA, he went to DESI, where he had many works with Géraldine, and still working with Géraldine Servan on these topics that he's going to talk about. And after DESI, he went to Barcelona, to IFAE, where he worked with Alex Pomarol, and where he's right now. So we're very pleased to have Benedict to visit us. And he's going to give this set of lectures. Oh, I have to record this, sorry. We're going to record the lectures. Just 1 second, because...
Shall I use this microphone here?
Yeah.
That's important for the recording. Sorry, went around the introduction, so you are?
Dishka. I am a postdoctoral to speak.
Yes. Thanks for coming. And you? Gabriel. Student here.
Student here, yes.
Wow, okay. I'm going to pass around this thing for you to put your names, because this is important in order to get to tell that we have a crowd here. Basically that. And this is important to have other courses in the future. Actually, if you would like to have other courses in the future, just let us know what topic do you want, even who do you want to give the course, and we can contact people and invite them to come here and give some lectures. So this is for the first day. If you can put your name and your institution. Put my institution here. And we go around. So Benedict, yes, please, can you start?
Okay, yeah, thank you very much for the invitation. Very happy to be here. First time in Sao Paulo. Haven't seen much yet, but it will come. Yeah, maybe. Okay, let me first. So the title of the lecture is. So I want to talk about cosmological phase transitions in the early universe and gravitational waves that in certain situations are generated during these phase transitions. And I also want to talk about discovery prospects in current and future gravitational observatories. So actually, before I start, so I assume some QFT knowledge. I guess did you all have QFT, right? Or, okay, good. Yeah, and if there are any questions, just feel free to interrupt me anytime during lectures or after lectures. And you can also just come to my office. I sit in room 102 here in this building. Ask something. Yeah, so the outline will be like on the announcement. I'm not actually sure I will do it in this order. I've never given this lecture before, so but I'm planning to cover everything I promised in the outline, but not necessarily in this order or in this like dream. I give a lecture. Okay, and so I'm not really using any particular reference. The one I'm most relied on is, well, it's originally a book, but you can also find it on the archive. It's a very nice finite temperature field theory. You never talked about this, did you?
No, he never gave a lecture.
Okay, so yeah, it's you can find it in archive. So it's at pH, and then 99013. 12. Yeah, and then I also rely on some research papers that will, I will give the references as we go along. So, okay, let me start with, to set the stage, let me start with like a very brief history of the universe. Universe. And so it is widely believed that like what set the initial stage of the thermal history of the universe was the phase of inflation. I guess you probably heard of this, but this solves, I'm sure you also heard like several problems, like the flatness problem, the horizon problem. It also can generate the density perturbations. And yeah, it's a rapid expansion of the universe. So if you start with some temperature, at the end of the inflationary stage, the temperature is essentially zero, right? And then it is assumed that there is a stage of so-called reheating, where the energy density that's stored in the inflaton is converted back into standard model of thermal plasma. And the corresponding temperature, the highest temperature that is reached during the stage is called the reheating temperature. So this is kind of the highest temperature that we have to consider. Inflation and then reheating to temperature. Now everything I'm saying depends a little bit on how high this reheating temperature was. So it's actually not so constrained. My understanding is that it can actually even be as low as the temperature of nucleosynthesis. So then many of the things I'm saying now will actually not have taken place. But for the following, I just assume that the reheating temperature is so high that we start at very high temperatures, and then so then the universe expands, temperature drops, right, and eventually we reach temperatures of water 10 to the 50 Kelvin. It is. I'm using natural units as usual, so it's 100 GeV in natural units. Yeah, that's where electric symmetry magnitude is.
Sorry? So it's GeV. Yeah, please feel free to ask.
Yeah, exactly. So yeah, GeV. Is it readable? I haven't been trouble writing with this, but is it? Shall I write it bigger or? That's good. It's okay.
So I have a question. So you said that this reheating temperature would be as low as the nucleosynthesis temperature.
Yeah, that's kind of.
So then, if it is anyway, then how do we have this electroweak symmetry?
Well, then essentially you already start in the broken phase. So you are in the broken phase, but you never have this phase transition. Well, or the phase transition, I guess, happens while you are reheating to this low temperature. So the XUV gets its breath. Well, actually, in this case, you already are probably in this broken phase during inflation. I'm not sure. Yeah, I'm not exactly sure. I mean, but anyway, there's no phase transition like in the way that I want to discuss. So, I mean, this is just a caveat to say that you have to assume that the reheating temperature is sufficiently high. So this is not a very strong assumption. So, okay, so electric symmetry is broken, meaning so the story. SU2L times U1Y is broken to the U1F. Actually, I could given other phase transitions, in particular if the electric gauge group was unified into great unified theory, a GUT, then one expects that at some higher temperature, typically what one would assume is that Kelvin, 29 Kelvin, which corresponds to 10 to the 16 GeV. There was maybe, and that's a very big maybe, nobody knows, a GUT phase transition. So that. So you have a grand unified theory, like say SU5 for example, is one well-known example, and that breaks to the electric gauge group. Let's see two outcomes. That's just to give another example of a possible phase transition that would definitely use. And then yet another example is that if you cool down further to temperatures times 10 to 12 Kelvin, which corresponds to 200 MeV. You have the so-called QCD phase transition. Where QCD confines, and also there's a characteristic in QCD, which is also okay, then you cool down further, and you can synthesize happens through combination and other things, but that's not really what interests us. So these were just to give some examples of phase transitions in the universe. What I will focus on are phase transitions like the electric phase transition, or potentially the GUT phase transition, where you have which can be described by a scalar field, which acts as the order parameter, which obtains a vacuum expectation value. I'm not sure this can be done for the QCD phase transition. Describe it this way. Okay, so let's take as an example the Higgs potential, or the electric phase transition. So, example, electric phase transition. Actually, let me just abbreviate phase transition to PT, so that I don't have to write so much. I will write phase transition quite often during these lectures, I guess. So the Higgs potential. At zero temperature, and I'm also assuming ignoring any radiative corrections, which is given by the usual, I think, Weinberg potentials. No additions. I feel this is a doublet, but now to keep it simple, let's just take one direction. So this direction contains a vacuum excitation value. This is a standard story, right? So you have a tachyonic mass term. So this m squared is positive, and is of the order the electric scale, right? 100 GeV. And so this term is positive, and this is also positive. This body coupling is also positive. Okay, so if you draw the potential now, let's see if we can do this. Let's put here. Draw the potential now. We have H, and so for it's a standard story, right? So for small field values, this term dominates. So I'm going down in potential. And then eventually, because this grows faster, this term takes over, and the quality coupling is positive, so I'm going up again. Right? So, and the minimum is essentially given by, it's the mass parameter of lambda. If lambda is order 1, then this is roughly so at 0 temperature, the Higgs sits here, it's basically red. Okay, but now at non-zero temperature, we will see that there's a correction term in the potential. The thermal correction to the potential, and there's a term which goes like t squared, h squared, and then there's other terms. So there's a mass term with a constant c, which is positive. Which is volatile with temperature. Right? Okay, so then if I'm at very high temperatures, let me define, okay, so now let me define a combined potential, right? So the point of ht is just V of h, this one here, plus the thermal correction. Okay, and now let me plot the potential. No, plot it in a different space. So let me plot V of h, and then t much larger than 100 g. So far above the electric scale. The temperature is far above the electric scale. And it's easy to see, right? I have this here, this term here is much bigger than this term. So the dynamic mass term is irrelevant, and potential is also like this. I'm sure you've probably all heard of this before, but anyway, let me just repeat it. So this means if we are at very high temperatures, then initially we are stuck in this value, right? So the electric symmetry is unbroken, zero electric symmetry is unbroken, and then if we cool down, we end up in this value, electric symmetry is broken. That's the electric phase transition, right? Okay, but now the question is, what happens? How do I go from one side to the other, right? And there are essentially two possibilities. One is, let me try and draw it pretty well. So one is that I kind of have like a smooth change. So now I'm going down in temperature here, right? So I have a smooth change. So the minimum here is at 0. Now here it's at some small non-zero value. And this value like gradually increases. So it's now here. So the point is there's a smooth change of the minimum of the potential until I reach this one. And this is called a second order phase transition, or also and this is actually, as we know now, if you just have the standard model, this is actually what happens in the standard model. So this is, essentially now since we know the Higgs mass, so this is kind of fixed the parameters of the potential, and you can calculate thermal corrections, evolution, and you know that this is actually what happens in the standard model. But as we also discussed later, there are ways to modify the Higgs potential in a way that something else happens. Namely the following. So you start here, and then what happens is that you see like a bump happening here. And the bump becomes bigger. So you have a second minimum period during the evolution. And then eventually you have a situation like this. So they are, at some stage, there are two minima, and they are separated by a barrier. And this is called, yes, a first order phase transition. And this is the kind of phase transitions I want to focus on in these lectures.
So if you have questions, you can ask, right? I'm just telling them that you can ask questions about these pictures.
I just have a question.
Sure.
How do you calculate the thermal delta V dispute potential?
Sorry, how do I compute?
The thermal correct.
Exactly. So this is kind of the lectures, right? So this is what I will discuss during the lectures. I was actually about to say this. So exactly. So what we will have to do in these lectures is exactly develop this formalism, right? To how to calculate thermal corrections to the potential. And then there's another thing. So let me just, before I say this, let me zoom into this picture, right? Like there's a stage. So we have some temperature where I have this situation. So I have two minima in my potential, but since I started off in this minimum, the universe is still, so the universe is initially stuck in this minimum. But then, as you all know from quantum mechanics, if I have this situation where I have a minimum which is actually deeper, I can tunnel into this minimum. So there's a tunneling process that brings me from this minimum to this minimum. And this is usually called the false minimum because it's higher, and this is a true minimum. Yes. Okay, and this is the other thing we have to do. So yeah, one thing, as I said, is one thing I will do, not this time I think, but probably next time, develop a formalism how to calculate thermal corrections to the potential. And then you will see under which situations you can have this barrier, right? So this, as I said, it's not a generic situation. You have to, it depends on your model. Yeah, so this is one thing, we have to calculate thermal corrections to scalar potential. And then we will also have to develop a formalism to calculate this tunneling, the tunneling rate. And then this will allow us to describe kind of the proceeding and the completion of the phase transition.
So just to mention, you're going to cover this too, but in addition to thermal corrections, there are quantum corrections. So all these pictures that he has drawn, they're the classical Higgs potential, let's say, or the potential. And then there's quantum corrections that
exactly.
Benedict will cover. So there are two types of corrections, thermal and quantum.
Exactly. So actually, I will during this lectures, I will first start off with zero temperature quantum corrections. I will say more about this in a few minutes.
Sorry, one more question. So you said that the thermal correction constant is positive. So is it always the case that this C turns out to be positive, or it is?
Sorry, sorry, what do you mean?
Oh, so the
this coefficient you mean?
Yeah, when you added, you said C is positive, so then it makes.
So actually, that's a good question because actually there are situations where it's not positive, where it's negative. Let's see, maybe if I have time, I can also talk about this. So it's actually something that has become fashionable in the last few years. It's called symmetry non-restoration. So, because if this happens, if it's negative, then actually you don't have the situation. Then you already at high temperatures, you're always in this phase. So it's a situation where you can heat up to high temperatures, but electric symmetry is unbroken. Yeah, it's a very good question.
Also, the picture that you may have in mind is this magnet, ferromagnet. I'm not sure if you saw this. That at high temperature they are disordered, so on average it's zero. But when you cool down, at some point they get aligned and you have a symmetry breaking because you pick up a direction. So you have this intuition that at high temperatures symmetries are restored, And that's the case when C is positive.
Exactly.
But as Benedict was saying, there are cases where symmetry is not restored at high temperatures. And that's, he has worked on that. So.
I'm actually, at the moment I'm working on this actually, so it's one project of mine involves this. Yeah, let's see, maybe, exactly, so maybe I'll discuss this also in some more detail later, in later lectures.
The potential that you write, it generates the first or second order phase transition.
So this one here is a first order phase transition. Yeah?
But the one that you write in the middle of
This one here, or
this V8 plus delta V8T.
I mean,
Is this a second
this is actually not really enough to know because the barrier arises from. So in the case of the Higgs, the barrier can arise from higher order terms. So there's a term that goes like h cubed.
Yes.
Okay, yeah,
I
okay.
would say that to generate barriers.
Exactly.
He said we will talk about quantum corrections. Then I thought maybe the quantum corrections will generate an H.
So there's different ways, and I'm planning to kind of eventually lay out all the ways that you can generate the barrier. So there are different ways. I mean, some can involve the zero temperature, some radiative corrections. I mean, it's an interplay of different terms. So, but in case of the Higgs potential, what you have, I mean, what could generate the thermal barrier is a term that goes like h cubed with some constant, and this constant is negative. So you see, if you have this term, then where are we? Exactly. So then, first initially the thermal mass term dominates with this positive constant, so you go up. Then the HQ term dominates with a negative constant, so you go down again. And then eventually the quartic coupling, the tree level potential will take over and you go up again. Right? So, yeah, so getting a barrier is always kind of like, you always play this game of like you have like one contribution to the potential that for small field values brings you up, then another one that brings you down at larger field values, and then of course you have to stabilize the potential, so you have to go up again. So, exactly.
Sorry, a quick question. The way you drew the picture of second order phase transition, it looked like it doesn't have a barrier.
Exactly, that's the point, right? So in effect, second order phase transition, you don't have this barrier. So this is really what separates the two cases. So first order has this barrier, second order doesn't have this barrier. So a second order phase transition is characterized by like a continuous change of the Higgs wave. So you start off with zero Higgs wave, and then it just continuously changes to the Higgs wave today. Whereas for a first order phase transition, you have this tunneling process, right? Like it's a much more violent process. So actually, sorry, I should say, so just to make this clear, so this term arises in the Standard Model for the Higgs, but it turns out that it's not big enough to give you a first order phase transition. So in the Standard Model, then you can add new fields to kind of give new contributions to this term, for example, and then make it first order. I'll talk about this.
Why do you want to have a bigger bump? Why do you want to go?
Okay, I'll come to that. Yeah.
Because he wants gravitational waves.
Exactly. So there are two. Okay, let me. Okay, exactly. That's very good. So okay, let me describe what happens here. So then we'll come to why I want this situation in the first place, right? Okay, so if I have this situation, then the phase transition proceeds by tunneling. And I mean, tunneling happens not everywhere at the same time. It happens there's a probability, and then at certain regions in space, the probability is high enough so that it happens, right? So what happens is that initially I have kind of regions in space where the field has already tunneled, and I'm in the true vacuum. So I'm here already. Whereas outside, I'm still in the false vacuum. I'm still stuck here, right? And these are called bubbles, and they are very similar to the bubbles that form during in boiling water, for example. So it's also first order phase transition. so now like, these regions appear like these bubbles, and then subsequently they start expanding and turn like larger fractions of space into the true vacuum, so into this vacuum here. Okay, then I can also have other bubbles that appear. Different bubbles. They all expand. Then you can already guess what happens. I mean, eventually they overlap, they collide, and eventually, like, the whole space is filled by the true vacuum. The phase transition completes, right? And there are two interesting phenomenological applications of this situation. Okay, let me start with the one I'm not going to talk about in any detail. Of first order phase transitions. And one is baryogenesis. So you've probably also heard these so-called Sakharov conditions. There's three conditions that have to be fulfilled for the mechanism to generate baryon symmetry. And the third Sakharov condition is a departure from thermal equilibrium. And yeah, this is kind of like a very big departure from thermal equilibrium, right? So this can actually be used to generate the baryon symmetry, and the most famous mechanism is so-called electrolyte baryogenesis. Yeah, and this kind of works at the interface of these bubbles. You can generate a baryon symmetry. In principle, already in the standard model, but as I told you before, in the standard model, the phase transition is not first order but second order, so it actually doesn't work like this. But then, as I said, you can modify the Higgs potential to turn the phase transition, to make the phase transition first order phase transition. That has been a big motivation for people who look into these models to study ways to make the electric phase transition first order. So, but anyway, this is not. I'm not going to talk about this. Instead, what I talk about are gravitational waves. Which are another consequence of first order phase transitions. Namely, I mean, it's already intuitively clear, I would say, that if you have these bubbles and they expand, so first of all you have the thermal plasma outside here, which is driven in front of the bubble walls, and then so you have plasma waves like going through the plasma, and these plasma waves collide. And then these collisions can cause ripples in space-time, and these are essentially gravitational waves. Right? This is one way. And then another potential source of gravitational waves are collisions of bubble walls, like these regions that separate the true vacuum from the false vacuum. Exactly. So, okay. I mean, this is all qualitative. I'm planning to discuss this in more detail later on. I just wanted to give the rough picture.
Sorry. Is there an argument for why point in false vacuum adjacent to a quantum true vacuum will decay more probability to true vacuum?
Well, no, I mean.
Because this is why the bubbles are expanding.
No, so essentially, yeah. I mean, essentially, you are tunneling. That's like the nucleus, so to say, of the bubble. And then afterwards, it's not a tunneling process. You're just kind of. I mean, you can think really of like a bubble whose walls expand. I mean.
Yeah, but for that, it's kind of well, it
I mean, essentially you gain energy, right? So it's really, you gain energy by turning the false vacuum into a true vacuum. So
yeah, but like in matter, there are processes such as this when we have I don't know undercooled liquid, and then we just wrap it, and then it starts circulating at certain points, and they like expand like bubble like. But here it's a vacuum. I don't see why vacuum is interacting with another point. Because the bubbles are expanding in such a way that it seems like a point adjacent, a false vacuum point adjacent to a point, true vacuum will have a greater probability of expanding. That's how I see bubbles
But
expanding.
if you're perturbing the system, you have a high probability of going
But it's
like
exactly. So you're going
you go
over
through you go through the barrier and you go to the true main.
yes, but it's vacuum. How vacuum is interacting? Does vacuum interact?
I mean, so
It's not interaction, it's just a matter of energy. So
it's just exactly.
true
So
vacuum has lower energy. So once you go to the true vacuum,
Yeah, but it's.
I mean, it's essentially you're just going to a lower energy state, right?
it's
So
free,
it's,
free
it's-
energy,
it's-
whatever you want to call it.
or free energy, exactly. So you get a free energy state by
Well,
by
agree with that.
expanding these regions.
But
So
why isn't this transition like, I don't know, random points and just like here we have a point that transitions
no, this is of course what happens, right? So you have, I mean, these are these tunneling events, right? So these are kind of these initial
These are random points.
critical bubbles. I mean, well, these are regions, right? I mean, it's never exactly a point. So these are regions, regions in space. If it's too small, they actually collapse again. So you have to. I mean, essentially, the way to think about it is that you have a certain surface tension, energy density in these bubble balls, and you have to compare that with the energy difference between the true and the false vacuum. And whenever you make these bubbles bigger, you actually gain energy. That's a way to see it. So the energy density that is stored in the bubble worlds.
Yeah, I see, but I wouldn't expect bubbles at all if a point adjacent to a false vacuum point adjacent to a true vacuum point didn't have a greater probability of decaying true vacuum. The big bubble-like expansion needs this to be true. Maybe it's
Okay, I don't know. I mean, I'm not sure I can.
maybe
Okay, let's talk about that. I mean,
Okay,
yeah.
that's a good point.
I mean,
this would be
again,
also
essentially the way I think about it is that you kind of you're going from a high energy state to a low energy
Yeah,
state, so it's low free energy, right? So,
okay.
Think about water boiling, it's the same thing.
Water, like,
We can talk
water
about this.
interacts with itself, like.
let's maybe talk about that later. So we don't get stuck on this too long.
I have a question. These bubbles are forming like they are in since like the tunneling is a probabilistic process. Then these bubbles are being created like randomly, and then putting this. So the universe is starting to oscillate inside this bubble at different times, and put this also create like Minicourse like variable this kind of homogeneous that we have also in inflation.
Sorry, say again. What kind of
Like
density perturbations you mean?
yeah.
Yeah, I think in principle it can contribute to density perturbations. I mean, but I think contributions are small. That
Since we have like for example, I could consider like a clock field
Uh-huh.
each of these bubbles, and when everything starts to get together, then we have an homogeneous in the space-time as we have.
I mean, you generate gravitational waves, which also kind of perturbations in space-time, right? So for that reason, I would expect that you also generate scalar perturbations. But yeah, I guess they are too small to have any significance, at least in the phase transitions that we consider.
Okay.
So I think that's really. I'm not sure if this has been discussed. discussed to, like, as a way, probably there are mechanisms where you use this to actually generate the density perturbations. I mean, like, say you have a inflationary stage that is not effective in generating density perturbations, you need something else. And, you know, I could imagine somebody wrote a paper like this. Okay, so this was the introduction. And now let's start in earnest. Okay, so as I said, I mean, essentially the goal is now to develop a formalism to calculate thermal corrections to scalar fields, right? And then you also have to determine how to calculate the turning rate, like through the barrier in the first order phase transition. And I will also say a bit about how the phase transition completes. This was very qualitative, right? This is more quantitative. Yes. And then eventually you also want to talk about gravitational wave sources and how they can be detected. But before going there, I will actually just set the temperature to 0 for now. And I will ask a question. So, given a tree-level potential, of some, we'll always do this for a scalar field in level 5, and the 0 here just means 0 loop. What are the radiative correction? Well, say this. Corrections to this potential. And there are two reasons I will discuss this in some detail now. One is that so the formalism that I will develop, and maybe you already know, so that is just a review, is easily, like, allows you to easily generalize to non-zero temperature, so it's a good stepping stone to go to non-zero temperature. The other reason is that the first model that I want to discuss, actually it turns out that the radiative corrections are very important to describe the phase transition. So we'll discuss a model where already the 0 temperature radiative corrections are very important. Yeah, this, so, okay, this goes under the name, sorry. Do I have 3 now? The effective action and effective potential. So may I ask who of you has heard about this before? Knows that you, this is usually done in QFT2. But yeah. Okay, so yeah, so I have to warn you, it's a little bit formal the next few minutes. As a student, I found it quite a bit confusing, I remember. But anyway, at the end, so even if it's not so clear at the end, I will just come up with a nice recipe that you can just use later on. And then eventually you should go back and try to understand the missing steps in between. But just to keep you interested, in the end there will be a very simple formula that you can apply even if you don't fully follow. But I mean, hopefully it's all clear. It's not so difficult. Okay, so the basic objects in QFT are correlation functions. and then they act on the vacuum, which is, I use this notation here to denote, to make clear that the vacuum of the interacting theory is zero. And from this, you can, for example, with the LC formula, you can extract S matrix elements and then calculate cross section. Okay, that's right. So this is what we want to calculate in 15. So here, actually, what we were interested in is the one-point function. So just one field operator. And here I can get rid of the time ordering because there's only one space-time point. And this is kind of like, this is kind of like the quantum version of the field in the three-dimensional potential. So this value, if we can kind of calculate this value, it will tell us the ground state of the theory in the interacting theory. So the goal will be to determine a kind of potential for this object that I can minimize to determine the value of this one-point function. It's a vacuum expectation value, right? So an operator sandwich between two vacuum. For the Higgs, this would be kind of the Higgs wave, right? So for example, this would be, so given input parameters, I could calculate the Higgs wave after taking the Higgs wave at the minimum of the potential after taking the one operations into account. Okay, so goal is to find potential for this object. Okay. Okay, so now what we have to do is, okay, first of all, just as a to remind you, I can calculate these endpoint functions, the correlators, and I'm using the path integral formalism. So, path integral formalism. Master formula that tells you how to calculate this object. I guess this you probably all seen before, right? So there's a path integral, meaning like, it will not really matter much later, but let me just remind you. So I'm essentially integrating over classical field configurations, right? All classical field configurations that you can have. And in the numerator, I have to insert these fields. These are all classical fields, different points. You multiply this exponential, and then I have to divide by this exponential again, integrated over all configurations to normalize it. Okay. For phi-4 theory, the action is just x. Term. This is actually an example I will use for today and next time, the usual phi-4 theory. So this is a two-symmetry imposed to forbid the phi-cube term. So the symmetry of phi goes to minus phi. And I'm using mostly minus metric, so just specify this. Okay, Anyway, so now we can generate, we can define the so-called generating function. Which is usually abbreviated by this letter Z. Okay, let me first define this object, and then I will tell you why it's interesting. So, I have the path integral again. Now I write phi, and then so this is essentially what this object I have in the denominator, but now I add this term here, and J is a so-called source. It's just a function that is arbitrary at this stage, and that's useful for the following reason. So now I can now I can use the following formula for functional derivatives. Right, so these are functions, and if I take the derivative of one function with respect to the other function, I get a delta function. This is kind of the generalization of the usual derivative rule. Okay, so then we get. Let me just write out this object. So let's add the derivative on this exponential here. Okay, so let's work out this derivative. So it's an exponential, so I first get the same exponential again, as usual, and then I get the derivative of what is in the exponential. And the derivative of what is in the exponential is just using this formula. I can replace this by another function. So what I get is x. This object here is just. Okay, so the lesson is acting with a derivative on this object here brings down one field. I probably guessed this already. So, meaning now if I act with n derivatives on this object, I bring down n phi fields at different points. So this gives me the numerator here. And then I have to divide by this object with j set to 0, and I get the denominator.
Do you have an IFAE convention in the second term as well?
Yeah, so yeah, I should just yeah, this just got mentioned because again it's really from the j, I guess, but okay, so then we get this master formula. Correlators. It's given by the nth derivative of this generating function with respect to j. And then I take the derivatives with respect to j at different points, so j at x1 to j at xn. And this brings down these fields here. Okay, and then, yeah, in the end, this still depends on the current, so I have to set the current to 0, which is a mathematical trick at this stage. There's also a factor minus I to the n that I have to include. and I have to divide by the solidization factor. The generating functional at 0 current. Right, so this is just, yeah, and it's, now it's clear why it's called generating functional, because it generates the input functions. So I guess probably you've all seen this before. Or? Okay. So far, it's not much. And are there any questions? Or it's fairly standard, right? So, okay, so now let's define this object here. It's sometimes called the energy functional. So I take the logarithm of this generating functional. And then minus I is just a convenient factor in front. Okay, and now I take the derivative of this object with respect to the current. Then, so the log here will, the log will give me a 1 over z. And minus I 1 over z of j. And then times the derivative of j. And the derivative of j is just this formula here, and this is just the one-time function. So this is why we kind of had to introduce this object. So the derivative of this functional gives this one-point function, which is the object that we kind of want to construct a potential for. So actually, it gives the one-point function for if I set the current to 0 here. Right, this was kind of, the current here is just a trick, so I have to kind of set it to 0 at the end. But it will be convenient to just keep it non-zero at this stage. So let me denote this with a j. So this is not the true vacuum here in general. This is kind of the vacuum in the theory where I have a non-zero current. That is, I have this. I have this term essentially, this extra term in the action. And so, okay, and now the trick is to perform a Legendre transformation. Just to remind you, I mean, the Legendre transformation allows me to, if I have a function f of x, it allows me to get, it gives me a new function, it's called f star of, what we call the derivative of x u, and I can obtain a function. It gives me a function of the derivative. Right? So we rewrite. It's a rewriting of the function in terms of the derivatives of the original function. I mean, this is used many times in physics, right? Like for example, the Newtonian, the Lagrangian, the Legendre transforms of each other, and so on and so forth. Yeah, now you can already see kind of why this is what I want to do, because I just said we have this function here. We want a function of this object, right? So, which is a derivative of this energy functional. So, by doing this Legendre transformation now, what we will get is a function of this. Let me do this here. This space. So what we now introduce is this so-called, this is the so-called effective action. I will denote this as phi with an overbar. And this is usually called the classical field because it's kind of there's an operator sandwich between the vacuum, so it's kind of like a classical object. Right? So, okay, so let me just write the definition. I start with this object as a function of the current, and now, as usual in the Legendre transformation, I subtract the product of the former dependent variable and the new dependent variable, which is phi bar, which is just the derivative of this object. So it's essentially it's the derivative of this object with respect to j.
It's phi bar of x, right? It's phi bar of x.
Yeah, I should be right. So here it doesn't matter, but here I should have x. Sorry, anything else? Okay, and I mean, so essentially how this works is I have this function as a function of j, and there's another j here, and now I need to use this relation here I can invert this relation to express the current in terms of this field. So I use this relation essentially to express j as a function of phi. I kind of invert this, so I write this current as a function of this phi bar, and then I plug this in, and I have a function purely of this classical field. Okay, sorry, this is quite formal, I know. Let me just, okay, I hope it becomes a little bit clearer now, because now let me just show you. So now let me take the derivative. So now, I mean, I have achieved, what I have achieved is I have a function of this classical field, which is kind of, yeah, it's kind of the tree-level field including quantum corrections. That's how you can think of it. So, and now let's take the derivative of this. With respect to phi, for the classical field. Okay, so first I get the derivative of this. J is a function of phi, so we can kind of evaluate this in a second. So this is the first term. And now, acting with a derivative on this here, on this here I get a delta function, right? So, acting with a phi derivative on this term, I get a delta function. And if I integrate, I just get, let's say, phi of y. J of y. And I also get the derivative acts on the current. X. Y. Okay. Another point is I can rewrite this using the chain rule. depend on the exponential determinant. Okay, let's see what we did. So I take the derivative of this with respect to this classical field. It acts on here. This gives me the current, if it acts on this, and then it gives me this term, if it acts on this. And now I use the chain rule to rewrite this as the derivative of j with respect to j. And then the derivative of j with respect to, again, this classical field phi. Okay, and now you see that this is, again, by definition, this classical field. So this term cancels exactly this term. Yes. This cancels this. And I end up with minus g of y. So more calculation to show us that the derivative of this object with respect to this field is the current. Okay, now we're almost there, because now the physical theory has a zero current. I mean, this was just like a mathematical trick that I added. So in order to obtain the physical vacuum, I have to set the current to zero. And so what we find is that, like, the vacuum states of the theory vacuum states are determined by this box around it because it's on the result. Okay, so just recapitulate. We have constructed, so we started from this object that was derivative is kind of the field was value we want to determine, right? Which includes all quantum corrections. And we've performed the Legendre transformation to this object here, this so-called effective action. And now we've shown that the derivative of this effective action with respect to this field is zero exactly for the field configurations that are kind of the vacuum of my theory, so like the ground state of my theory. So by calculating this function and then finding the cell points or minima, I guess, I can determine the vacuum.
So at this point, the vacuum can be x dependent, right? There's nothing. At this point, the vacuum can depend on
exactly. So
the position.
At the moment, still, it can depend on the position. So there are theories where you have x-dependent vacuum, like you have solitons or other objects, right? But of course, for our purposes, it will be enough to consider vacua that are space-time dependent. Then there's a further simplification. I still have a little bit of time. That's great. So can I erase this? Or are there any questions? I mean, was this roughly clear? I mean, otherwise, just continue to ask. I mean, the main message is really this kind of: I've constructed this object. Was derivative gives me the ground state of the theory. So that doesn't tell me yet how I calculate this object, we will come to that, right? But at least I know an object that kind of I can minimize to determine the ground state of the theory. So actually, yeah, let's.
It's really the quantum vacuum, right? That's important. It's the quantum vacuum.
Exactly, it's a quantum vacuum, right? It's kind of including all quantum objects. That's kind of that's kind of what it makes it. It's much more than the tree level potential, right? It includes all quantum corrections. So the tree level potential, the minimum, doesn't tell me anything about if quantum corrections maybe change the minimum. So this object, by definition, includes all quantum corrections. Okay, so now let's specify to space-time independent. Space-time independent configurations. Yeah, okay, so what we are interested in is configurations where phi of x is, let's call it, let's say phi c for constant. Sometimes this is also used for classical, but I think it's clear. Independent of space-time, right? So just a homogeneous configuration. Okay, then I can so this is a function of space-time, right? So in general, I will have some kind of, this will involve an integral over space, right? Because it's just a function. And this is just a number where this in general is a space-time dependent object. So it will involve an integral over space. And then times some function. This is for classical information. I have a constant configuration that depends on this. And for convenience, we define this as minus. Yes.
So I have a question like followed by this dependence of space-time on phi. So when we have this bubble nucleation, so we will have spaces with true vacuum.
Exactly. So this will be discussed separately. I mean, so for now, I'm just interested. Exactly. Later on, we will discuss also space-time dependent configurations when we discuss tunneling. But for now, I'm just interested in kind of determining the vacuum of the theory, right? Like. Okay, so the point is kind of I can write this as an integral over space times some function of this field. But now, because I'm interested in configurations which don't depend on space, I can kind of invert this. I can write this like this. Right? Because this doesn't depend on space. So this will just give some formally infinite constant that I have to divide out. And this is the object that we are really interested in. So this is called the so-called effective potential. So for constant field configurations, we can kind of, from this effective action, by dividing a formally infinite constant, we can define this so-called effective potential. And now, the vacua of our theory are again given by. So let me just write it to make it clear. So now, the effective is the potential corrected by quantum fluctuations. This is a function we need to minimize. To account for the ground state of the theory. so in order to take into account the quantum corrections, what we have to calculate is this effective potential, then we can use it as a normal potential, right? We can just determine the ground state by finding the minimum, so just the effective and the derivative of this has to be 0. That's the ground states. Okay. Good. Any questions?
I didn't understand quite well what is related to the first equation.
Sorry?
The first equation is the potential of the effective action is potential time integral of
Volume of space-time.
It's the integral of the volume of space. It's like in quantum thermodynamics, it's an extensive quantity. So if you, the point is if you plug in a constant field into this object, you formally get infinite.
Alright, so basically...
And this is because of this integral over space-time over constant configuration. So what you have to do, you have to divide by this factor to get what you really want, like this effective potential value. And what you can do is you can kind of regulate it, right? You can make your space finite and then divide by this volume and then take the limit of space going to infinity. It's probably a mathematically correct way of defining this. But yeah, the physicists, we just divide by infinity, right? We don't no shame. Okay, so far so good. So now I told you what we want to calculate, and that has been quite abstract. And so now I will tell you how to calculate. Now here's a little more interesting. How to compute the effective potential. Okay, now I have to state something that I will not have time to prove. So you just have to believe me, but then it's written in all the QFT textbooks, so if you're interested in to see how it works, so you can have a look there. So this is our proof. And we'll just tell you that, so now let's go back to this effective action. And the statement is that this effective action is a generating functional again. So this effective action is the Legendre transformation form of a generating functional, right? So it's not so surprising that maybe this is also generating functional in the sense that it also generates correlation functions. And it does generate very particular correlation functions, namely the so-called one-particle irreducible correlators. And that's usually abbreviated with 1pi. This is, just to be clear, the sum of diagrams, defined as the sum of diagrams that cannot be separated by cutting one line. So which cannot be separated into two pieces. By cutting one line. So it comes with some definition, but it's very useful. So to get some example, for example, if I have diagrams like this, and I'm scalar 543 again, corrections correlator which go like this. And of course, those are 1 pi. Because if I cut one line, I cannot separate it into two pieces. On the other hand, if I have direction like this, those diagrams are not 1 pi because I can cut here, for example, I cut one line, and I get two diagrams. Right? Here I cut one line, and I get two diagrams. So these are correlators. The effective action is a generating function for correlators, which are the sum of these 1 pi diagrams. And these you probably, and these are the objects that you renormalize. Right? I'm sure you've probably seen this before. Okay, you will see in a second why this is useful to know. Okay, so the statement is that correlators are sums of 1 pi diagrams. So let me just use this suffix here. So these are really, for the two-band function, these are just sums of these diagrams from these diagrams and corresponding to the five-band functions. And let me just introduce this useful short notation. Those are obtained from the generating functional by taking derivatives with respect to this field phi. So it's again similar to the generating functional that we've seen before. And then in the end you have to set this to 0. So this is very similar to this generating function as a function of the current that you've seen, right? Where you take derivatives with respect to the current. Here you take derivatives with respect to this field phi, and then in the end set phi to 0, and then you get these correlators.
It's not the log, right?
Hmm?
It's not the log.
No, there's no log. Sorry? Yeah, it's not the, I mean, it's a z, right? No, sorry, what do you mean? Like,
Yeah, no, that's what I meant, sorry.
Yeah.
It's like
Okay, and this is useful because, so I hopefully, let's see, how much time do we have?
5 minutes.
Okay, 5 minutes is good because I want to get to kind of the recipe to calculate this. Okay, this tells us that I can write this function as an infinite sum. I don't know if it starts, it probably doesn't start from 0. I'm not sure if it starts from 0 or 1. Yeah, it doesn't matter. I guess it depends on this. So let me first write this. Okay, so I'm using this knowledge now that I just stated as our proof, right? That this effective action is a generating function of these objects here. So if I take derivatives, I get these objects. So that means I can kind of represent this function as an infinite sum over these objects. So now you can check, right? If I take the function derivative, and then set the current to 0, I just extract a given correlator gamma n, right? So it's just okay. So now we we have to, so this is still for the, this is still for general space-time dependent currents, right? Sorry, classical fields. Now we want to specify to space-time independent configurations, right? This is kind of what allowed us to get the effective potential. Just bear with me for a second, and we're almost there. Okay, so the idea is now to go make a Fourier transform. And I will just tell you how this works. So integrate over momenta. So now I want to express these objects. I want to, instead of a position-dependent function, I want to express in terms of a momentum-dependent function. And this is because at the end we will use usual Feynman rules to calculate these objects, and they're more convenient in momentum space. So I'm going to do this. And to get this, I just take this and then express it as the Fourier transform of corresponding endpoint when PI function that is a function of the end momentum. That is essentially it's usually a Fourier transform that integrate all the momenta times the exponential, so then there's a delta function because of momentum conservation. Okay, so let me maybe abbreviate this a little bit, because in this one you can check yourself now if you, I give you this as an exercise maybe, if you plug this in here. So you plug this in here, and now you, so let's plug this into formula gamma phi, and then use that we are interested in constant field configurations. So we want these fields here to be space-time independent. Okay, and then I also need a very basic relation, maybe that so it's just a definition of the delta function. Yeah, so this I just leave it, you can try it at home. It's very useful. So you just take this, plug it in, you reduce it to constant field configurations. So you assume that these fields here are space-time independent. You use this definition for the delta function. Yeah, and then essentially you extract the effective potential, and you get this formula. And this will be kind of our master formula to calculate the effective potential next time. So this is what you will find, or should find. So the statement is that I can calculate this effective potential as an infinite sum over these endpoint functions, these 1pi endpoint functions. And then I have to multiply with the field to the appropriate power and divide by n factorial. And yeah, so you can essentially see that kind of I mean, it's already clear that, so if I mean, I'm going to momentum space, right? So I started with something which is space-time dependent, but now I specify to space-time independent configurations. And then if you go to momentum space, I guess as you all know, this corresponds to zero momentum, right? So it's already clear that you will get something in momentum space that depends, that doesn't depend on the momentum. Okay, then as we will see next time, so let's see, I think that's also it's a good point to stop. So as we will see next time. So this is really now giving us a recipe how to calculate this function. So this is kind of what I wanted to get at. Namely, these objects are, again, these are endpoint correlators, endpoint 1pi correlators. So they are given, for example, so let's give an example in phi to the fourth theory. Can I have 2 minutes? Then, yeah, so in phi to the fourth theory, for example, we have no. So the 2-point correlator is given by, I just have a normal propagator, and then I have this. And then there are higher loop corrections. So at one loop order, I just have these 2 terms here, right? And I'm corresponding to for the next object I have is it's a 4-point function. So if I do the fourth theory, I have a like this, right? And then I add a loop correction to this. So this gives us, I mean, so now it's kind of clear how to calculate these objects from family diagrams, right? So we write down all the 1pi diagrams at a given loop order, and I mean we will just be interested at one loop. That's again, now you have to work these Feynman diagrams out. It's quite simple because the momenta, the outer momenta are 0, right? All the momenta are 0, so I essentially just have an integral here over the momenta with some insertions of the vertices. Okay, so anyway, this is what we'll do next time. So then from this, essentially, then you can sum over these diagrams very nicely, and you get a very nice expression for how to calculate the effective potential in one loop. This is what I will do next time. Okay.
Thank you, Benedict. So time for a few questions.
Okay, I'm sorry if this was a bit formal, as I said. I mean, next time it will become, hopefully, a bit.
Yeah. People that arrive late, if they can sign up this sheet just first to have a control of some people that are attending the lecture, that would be great. So, yeah, so I think that's it. So see you on Monday. Nice weekend. You can ask questions also.
Exactly, so feel free to ask now, or others, or yeah. Again, next time I will try, so the calculation will be a bit less abstract, and hopefully a bit easy, more easily accessible.
Yes, we led Cosmological document. when you have a third